You are most Ricky, and who's the other official? Don't have it in front of me at the moment.
Sivanan
Sivanan, right? Sivanan and Ricky, I think, provide the official solutions. And one reason I like their solutions is they plotted K as well as the lift versus time. And K has an interesting structure, as you see from those official solutions. It starts off at 0 and goes back to 0 in finite time, reflecting the fact that there's a finite memory in the supersonic flow, which is actually true in both two-dimensional and three-dimensional supersonic flow, because the memory only goes back as far as it takes a fluid disturbance to go from the leading edge to the trailing edge, because once the disturbance reaches the trailing edge and moves past the trailing edge further back in the flow, it cannot change what's happening on the airfoil. So that time is the chord divided by the difference between the free stream velocity and the speed of sound. So, and then if you normalize it, normalize time, you can express that internally in terms of Mach number. It turns out to be Mach number over Mach number minus 1, which means it goes to 1 as Mach number gets very large. Of course, it goes to infinity as Mach number goes to 1. And for 2, it would have to be exactly 1 in non-dimensional time. And then, of course, it's a bit longer at Mach number 1.2. So that's interesting, and I hope you enjoy looking at their solutions. Are there any questions about the last homework? Hearing none, you have another homework assignment due today, which is to tell me all the typographical errors that we're going to correct in the next edition of our book. And by the way, we've begun to talk to the publisher about the next edition. So you are contributing to the literature by identifying some typos that we hopefully will correct. But today we want to talk about three-dimensional supersonic flow, and then next Tuesday we'll do three-dimensional subsonic flow. And it's mostly good news in the following sense. The methods that we're going to use to set up the formulation for 3D subsonic and supersonic flow will be similar to what we use for 2D supersonic flow. And I should, as an aside, tell you that these are not the methods by which those phenomena were originally developed. Those models were originally developed. The original approach was much more convoluted, and that's why I'm not telling you about it, although some of that is discussed in the text if you really want to know what people did back in the day. But we're going to do it much more efficiently. And then, so we're going to have a much more efficient development. That's a good thing. And probably the even better news is that there are now companies that have taken these formulations and developed computer codes, which they will happily sell you or license to you. So there's not much point at this stage for you to develop your own computer code, unless you think you have some other fascinating approach that will make computations even quicker. These codes for classical potential flow theory tend to run in seconds. And you may think that's fast, and it is. But if you're doing thousands of calculations a day, there's still room for making them even quicker. I once talked to someone at Boeing about the fact that we can now solve the Navier-Stokes equations in days rather than months. And he said, well, that's all very fine, but I need a faster potential flow code because we run thousands of calculations a day. What can you do for me there? But anyway, some people are never happy. So let's talk about three-dimensional flow. This is three-dimensional supersonic flow. And let's go down a little bit here. And so there's our governing equation, 4.2.33. We're going to do the special case of simple harmonic motion in time. You can see my cursor, is that right?
Yes, we can.
Okay, great. So we're going to assume simple harmonic motion with a frequency omega. And in principle, you can think of that as a Fourier transform in time, and we could invert it in principle and do transient motions. But as I discussed in our flutter analysis revelations, simple harmonic motion is what people mainly use, and even for gust response, using the ideas of power spectral density, they mainly use the simple harmonic motion result for unsteady flow. And all of these commercial codes for potential flow are almost entirely devoted to this special case. So anyway, we assume this is simple harmonic motion in time. We take a Laplace transform because it's supersonic flow with respect to x, and that reduces this partial difference equation in 3 spatial coordinates in time to still a partial difference equation, but now only in 2 spatial variables, namely z and y, having taken care of time by ei omega t and having taken a Laplace transform with respect to x. And here's this equation is to remind you what the Laplace transform with respect to x looks like. So now this is a partial difference equation for the Laplace transform with respect to x of the velocity potential. And mu is the same old mu we had for 2D flow. It's ugly, but not unmanageable, as it turns out. And so then the question is, okay, it's still a PDE, and whether we're doing it numerically or analytically, the only thing we really know how to solve is an ODE. So how do we reduce this PDE down to an ODE? And in particular, we need to do something with respect to the y variable. The y variable is in the span-wise location, right? This is 3D flow. So what shall we do in the span-wise variable? Well, we've been doing transforms, so we're going to take a transform. But in this case, we're going to take a transform that is a Fourier transform, not a Laplace transform, because in the y direction, things are happening for both positive y and negative y, and it turns out they're happening both on the wing and off the wing. And a Laplace transform really wouldn't work because that assumes that nothing is happening for, say, y less than 0, which is clearly not the case. And again, remember that a Laplace transform is a special case of a Fourier transform. So the general rule is when in doubt, use a Fourier transform, but it turns out a Laplace transform has done the job. Well, the Fourier transform will do the job too. But it's, of course, more efficient to use a Laplace transform if you know that's going to do the job. Okay, so we're going to take a Fourier transform with respect to y, which is going to reduce this equation 4.2.34 down to an ordinary difference equation, which we know how to solve. And gamma is the Fourier transform variable with respect to y. So here's the formal expression for taking the Fourier transform of the Laplace transform of the Laplace potential. For linear PDEs, taking transforms is definitely the way to go. Okay, so then we can write down formally the solution of this equation. It looks very much like what we did in 2D flow, except we have this extra factor, gamma, floating around, which is the Fourier transform variable with respect to y. Again, formally, we're going to think of this solution blowing up as z becomes large and positive, and we don't want that to happen, so we throw that part of the solution away. That's requiring that the solution be finite or bounded at infinity, at positive infinity. And by the way, if we wanted to know the solution below the airfoil at negative infinity, we do the same thing, except then we throw this solution away and retain this one. But from symmetry, once we know the solution above the airfoil with a minus sign, we have the solution below the airfoil. So anyway, what's left is this. And then we're going to determine B by solving or satisfying the boundary condition on the airfoil. And when we do all those wonderful transforms of the boundary condition, that means, I found a typo for you. Hope you found this too. This should be d phi star dz, not d phi star dx, evaluated z equals 0. and that's equal to the double transform of the downwash. And using that boundary condition and this solution, we obtain the expression for B. And then inverting, well, there's a solution for B. And then once we know B, we know the velocity potential itself. And at the special place, namely on the wing, at z equals 0, it becomes this. Otherwise, there's an exponential factor, which is 1 at z equals 0. And then we do a double inversion with respect to both x and y, and that's the solution. So we're done, more or less. Okay, but there are two things to do. We have to do a double inverse of this factor, and then, of course, we have to work out this integral. And note that at the moment, the integral over the dummy y variable, which is eta, goes from minus to plus infinity. The integral with respect to the dummy coordinate-wise variable c, well, still only goes from 0 to x. That is, if I'm in what's happening at a particular position x, y, I only need to know what's happening for some values of x less than x, or values of the dummy variable c less than x. But in the y direction, I'm still in a position of having to know everything from minus infinity to plus infinity at the moment, although that will change momentarily. So let me pause at this point. This is just thinking transforms, recognizing that when you do an inversion, you have a convolution integral, but now you have a convolution integral not only with respect to the chord-wise variable c, but the span-wise variable eta, because this is 3 dimensions. So there's more to the story, not a whole lot more, but there is more. And let me pause here to make sure that everyone's happy up to this point before I go on. Any questions or concerns at this point? Hearing none, let's press on. Now, what is the double inverse of this factor? I'm glad you asked. Well, first of all, we'll invert with respect to the Laplace variable. That's the one where we took the Laplace variable, Laplace transform with respect to the coordinate. Well, it's about what we had before for two-dimensional flow. There's this exponential factor, there's the square root of Mach number squared minus 1, and there's a Bessel function, except the argument of the Bessel function before it was just this first collection of terms, but now it has an additional contribution due to the Fourier transform variable with respect to the span-wise coordinate. So this is almost what we had before, but not quite. And where do we find this fine result? Well, we looked it up in Batesman's book on transforms. It's actually the same inversion we did before if you take into account the factor gamma. And then we need to, of course, go ahead and take this whole thing and invert it now with respect to the span-wise Fourier transform variable, gamma, as we need to take the inverse of all that. And this goes through some details of it, which I won't bore you with unless you really want to know. But finally, and this is what's interesting to some people, including me, and I hope to you, the double inverse of this factor, which is what we really need, is still this exponential factor, still m squared root m squared minus 1, but now it's the cosine function of all this stuff, okay? Cosine function of all this stuff, except that that's not the total answer. That's true when the absolute value of y is less than x over this factor involving Mach number, but this inverse, double inverse, is 0 when the absolute value of y is greater than x over this inverse. Okay? And note that although we had a Bessel function a moment ago, now we're this expression is entirely in terms of what I will call elementary trigonometric functions. It involves exponential and a cosine. That seems like it seems paradoxical in a way. It seems like we've ended up with functions that are easier in 3D flow than in 2D flow, but that apparent simplicity, in fact, is quite deceiving. Why? Because we've got this factor x squared over n squared minus 1 minus y squared, and this turns out this can be 0 in the flow field of interest. And so this value of the double inverse is singular because we have a factor in the denominator that can go to 0, which means this whole thing is going to infinity. But the mathematicians would tell us an integral singularity because it's only a square root singularity. And if I integrate this with respect to x and y to get something like lift or moment or whatever, I'll get a finite answer, which is a very good thing. Same thing happens in subsonic flow, as we'll see later on. But the flow field does have some singularities in it, but they're what a mathematician would call weak singularities. So what does this all mean physically then? If I use this double inverse and put it back in the convolution integral, there it is. I put this back in the convolution integral. This factor is 0 over much of the flow field, but not all of it. And we need to sort out when it is 0 and when it's not 0. And we also, if we were really writing the cubic code ourselves, we'd have to think about how we're going to handle that square root singularity. But let me show you a picture, which I hope will elucidate this more clearly. So here's the picture. And this is a famous picture if you do supersonic aerodynamics. So I'm showing, what am I showing in this picture? I have a triangle, which I'm calling a delta wing. We could have some other shape, but a triangle delta wing is a common shape in supersonic vehicles, and it's also a nice illustration of what we're dealing with. So we're thinking of this. We have a point on the wing, we'll call it xy. It's that point right there. And we would like to know what the velocity potential is there. And then we can always use Bernoulli's equation to compute the pressure once we know the velocity potential. But now we need to keep track of what we know and what we do not know, and where we need to know it. It's supersonic flow, so for x less than 0, or its dummy variable c, where x or c less than 0, the flow is undisturbed because this plane is moving at supersonic speeds faster than the speed of sound, and the flow field is not disturbed ahead of it. Moreover, any disturbance behind the wing, and there is a disturbance behind the wing once the wing passes through the air, it cannot catch up with the airfoil because any disturbance back here moves at most with the speed of sound, and this is moving faster than the speed of sound. So we don't need to worry about what's happening behind the wing either. So we don't need to think about what's happening behind the wing. We don't need to think about what's happening ahead of the leading edge of the wing. We certainly need to worry, however, about what's happening on the wing. And as I'll explain in a moment, we also need to worry about what's happening, or at least take into account what's happening off the wing in certain portions of the flow field. That special character of the double inverse that we saw a moment ago, which says that the double inverse is 0 off in a certain region of the flow, basically says that the only possible regions of flow that can influence what's happening at that point xy is a region that's inside this line and inside this line. What's happening down here cannot influence this point. What's happening up here cannot influence this point. On the other hand, note that what can influence this point includes all these flow field this flow field region, for example, as well as the one below, can influence this point. But there is further good news. the furthest most point forward, the leading edge tip, if you will, it also has Mach lines. That's what these lines are called. These has Mach lines that pass through that point, and this point can only influence the flow field inside this Mach line and inside this Mach line, which means that this part of the flow field is undisturbed. This part of the flow field is undisturbed. And as far as this point XY is concerned, it's the shaded region that can contribute to what's going on at that point. So we reduced the entire plane XY to a finite portion of XY, and that's a good thing. This is all good news so far. But there is one difficulty in 3D flow that isn't present in 2D flow, and that's the following. On the wing, I have a boundary condition that says the downwash is known in terms of the motion of the wing. That is, I know d phi dz at z equals 0 in terms of the motion on the wing. But off the wing, I don't know that. I don't know that. What I do know is that phi itself is 0. Actually, what I know is the pressure is 0, but for supersonic flow, that's equivalent to the velocity potential itself being 0. So on the wing, I know d phi dz at z equals 0. Off the wing, I know phi itself is 0 at z equals 0. And this is what a mathematician would call a mixed boundary value problem. That is, in some region of the boundary, I know one thing, d phi dz, and in another region, I know something else, namely phi itself. But that's just enough information to solve the problem. And there are certain analytical solutions for simpler problems that do come out of a mixed boundary value problem. But for this one, in general, we have to resort to numerical procedures. And the numerical procedure is easy to describe, not always easy to implement in terms of computer code. Basically, we do the following. We take the shaded region and we divide it up into little boxes. And we assume that phi or d phi dz is a constant within that box. And let's say the number of boxes is 100. Then let's say we have, I don't know, 60 boxes off the wing and 40 on the wing or vice versa. So we have 100 unknowns, namely, we either know the phi dz on the wing and we don't know phi, or we know phi off the wing and we don't know the phi dz off the wing. But the number of unknowns and the number of boxes and the number of equations that we get by taking that integral, that double integral, and dividing it up into little boxes and producing 100 linear equations, one for each box, is just the right amount. And so we have to do some linear algebra. We have to do some manipulation to make sure all the knowns are on one side and all the unknowns on the other side, but we can do that. Taking into account also the singular nature of the solution along these Mach lines, and these Mach lines are where that square root singularity occurs. So that's it. You've now become experts, at least in the formulation of 3D supersonic flow. Now, there was a time, and if we had more time this semester, we'd do it, when I asked the students to write their own computer code to perform the calculation I've just described. I know you're going to be keenly disappointed when I tell you that we're not going to do that this semester. But what you will have a chance to do in about a week's time is to use a computer code that has been professionally written to do this kind of calculation. Okay, so I'm going to stop here for the moment and see if there's some questions. Are there any questions about what I've just said? By the way, this solution procedure is called, not surprisingly, the Mach box method, since it's related to these Mach lines and how you set up the code. One of the early pioneers in this method was a fellow named Samuel Pines, And some people irreverently refer to this method as the pine box. But I don't know if you're old enough to remember that people were once buried in pine boxes, but that was considered a clever thing to say. But whatever name you give it, it's basically a matter of taking this singular integral equation, converting it into a set of linear algebra equations, and then letting the computer do the work. Any questions? Golly, are you still there?
Still here. Still here.
Oh, that's good to know. That's good to know. But if you don't have any questions, I've got time to do the subsonic case today too. You want me to do that?
Yes.
Why not? Okay, let's do the subsonic case. If we are in subsonic flow, all these wonderful properties of supersonic flow are not available to us. What does that mean? That means that the flow ahead of this airfoil is disturbed. Why? Because if I oscillate this wing, a disturbance moves with the speed of sound, and if this wing is flying at less than the speed of sound, that means the disturbance is propagating ahead of the wing faster than the wing is flying. And also it means once I create a disturbance back here in the wake behind the wing, it's also moving with the speed of sound. And if this is flying at less than the speed of sound, then this disturbance can catch up to the wing. So I disturb it back here, but then that disturbance moves through the fluid and catches up with. So what does that mean? That means that I cannot consider just a limited area of disturbed flow, as in the supersonic case. Now, effectively, the entire z=0 plane, everywhere is disturbed. And therefore, if I want to use a method similar to what I use for supersonic flow, I would have to put boxes over this entire region, and then presumably I would cut it off at some distance far away from the wing, far away being defined as far away compared to the size of the wing, right? And you could do that, and people tried that in the early days, and it's not a very efficient thing to do, but it was tried. And there are actually, I think, there's still a few codes out there, even the subsonic case, that do it this way, but we don't want to go there. Instead, in the subsonic case, after some consideration of alternatives, people came up with the following method. In the subsonic case, what we really know off the wing, if we have a lifting wing, which is the usual kinds of wing we like, what we really know off the wing is that the perturbation pressure itself is 0 off the wing, and d phi dz, the gradient of the velocity potential, is known in terms of the motion of the wing on the wing itself. So what people have done is they've come up with what I'll call an inverted integral equation, where the thing we really want to know, namely the pressure, is under the integral, and the thing we actually know on the wing at least, namely the downwash, is outside the integral. So let's see how that works. So here's Bernoulli's equation. This is the linear relationship between the perturbation pressure and the velocity potential. Okay? All right. So now let's derive an integral equation by transform methods and a solution by collocation. And again, this is not the way it was done originally, but the way it was done originally is described in the book if you're interested. But we're going to start out much like we did before for the supersonic case. We're going to assume some harmonic motion. In principle, you can extend this to non-simple harmonic motion, but that involves considerably more effort. Okay? And now we can't use a Laplace transform anymore with respect to x, because things are happening for x less than 0 in the flow field. So we need to use a Fourier transform with respect to both x and y. And so we're going to take a double Fourier transform with respect to x and y. And that's going to give us, oh, okay, we'll also take a double transform with respect to x and y of Bernoulli's equation. And of course, the pressure itself is going to be assumed to be subharmonic in time also. And so, for example, this P star is already assumed subharmonic motion, and then we take a double transform of it as well. And so this is a relationship between, this is Bernoulli's equation, but now transformed with respect to x and y, and assuming subharmonic motion. And then we go through the same procedure we went through for supersonic flow. So formally, the transform relationship looks just like it did before, where I'll show you what mu is in just a moment. It has a slightly different form because we're using a Fourier transform rather than a Laplace transform. But now we solve for the velocity potential. We then can find the pressure, which we know in terms of velocity potential, now in terms of the downwash. So this is the pressure transform. This is the downwash transform, and this is a factor that involves the transform variables. And now, if I knew W everywhere, I would just double invert this and find the pressure, but I don't. I only know W on the wing. So I manipulate this equation and separate out the downwash non-dimensionalized by the free stream velocity on this side, and I have the pressure on this side, and of course this factor. And then we double invert that. Now here's the downwash, here's the pressure, here's this kernel, and here's what the kernel looks like. And you could, if you were so inclined, write a computer code to evaluate this kernel. And I'll show you what the kernel looks like in a moment, because it turns out that you can actually work out this kernel in analytical form, just as we could for supersonic flow. But it's an inverted kernel in the sense that the thing we really want to know, which is pressure, is inside, and the thing that we do know to begin with, at least from an aerodynamicist point of view, namely the downwash given in terms of the motion of the wing, is outside. But this integral, which is formally from minus infinity to plus infinity over both c, the chord-wise dynamic coordinate, and eta, the span-wise dynamic coordinate, it's formally over. It's over the region from minus infinity to infinity in both cases. But this is the really good news. The pressure, the perturbation pressure, in fact, is zero off the wing. So this integral is really only over the wing itself. That's why we do this, because we reduce this again to a finite region in the flow, namely just on the wing itself. And we don't have to deal with what's happening off the wing at all. And by the way, you can do the same thing for supersonic flow, although this method was developed originally to deal with subsonic flow. And there are proponents of the Foxx method, which we discussed a moment ago, and this method for supersonic flow, and I won't get into who's won the battle of that argument. I think the battle still rages. But certainly for subsonic flow, this is definitely the way to go. Okay, so now the question is, how are we going to solve this problem? Well, we're going to probably try the same thing we tried before. Now we're having an interval just over the wing. We'll divide it up into little boxes. I'll have, let's say, 100 boxes. So I'll have 100 unknowns P. I'll have 100 knowns, namely the downwash at in the center of each one of these boxes. Now I'll reduce this linear integral equation to a set of linear algebraic equations, and I will have to invert a matrix, which basically means I have to invert K in its discretized form. But presumably, I should be able to get an answer. And that was tried early on, and didn't work. It didn't work. And it's a subtle reason why it doesn't work. It turns out in subsonic flow, although this is usually mentioned in a course on aerodynamics, in subsonic flow, the solution of this equation is not unique. There's a whole family, an infinite family of solutions. And so you have to apply some additional constraint on the equation to get a unique and physically meaningful answer. And what people usually apply is the kata condition, which if you've taken a course in study flow aerodynamics and subsonic aerodynamics, you recall that requires the pressure to be zero at the trailing edge. That's an empiricism. There's not a law, there's not a fundamental theory that says that should be true. In fact, mathematically, you could require something else. You could require the pressure to be zero at the leading edge. The only problem with that is it doesn't agree with experiment. So once experiments were available and they saw the pressure was tending towards zero at the trailing edge, they said, well, let's apply that condition. And this is true, by the way, in study flow and incompressible flow and 2D flow. I mean, this is true whether you're unsteady or steady, whether you're compressible or incompressible, whether you're in 2D or 3D, you need the Kata-Joukowsky theorem if you're Russian to make the solution unique. So what people did originally then was to take this pressure and rather than carving this integral up in boxes, they assumed a series solution for the pressure where each term in the series was chosen so that the pressure was zero at the trailing edge, right? Sort of satisfying the boundary condition through a modal form. And people worked on that for quite a while, and it works. But later it was discovered that you can get around all this with a method which is still not entirely rigorously based. It turns out that if you are clever, clever being the following, if I put the points at which the pressure is evaluated in each box at the 1/4 chord, and I put the point in each box where the downwash is evaluated at the 3/4 chord of the box, of each box, then the solution tends to satisfy the Kata condition and all is well. And this usually goes under the name of the doublet lattice method. Don't ask me why it was called that, but it is. And so there are now computer codes available using the doublet lattice method, as well as other methods which satisfy or solve this equation. And this gives you some of the details of all that. There's an alternative derivation of that integral equation in the book, which I'm not going to go through, which involves using Green's theorem. As you can see, it takes a few pages. And have I gone too far? No, not too far. I think I have one more. It takes a few pages to get it. There it is. It's an ugly looking thing for lots of reasons. Here's the K function multiplied by y squared, and that factor is important, as you'll see in a moment. Here's the Mach number, here's x, here's y. R is actually essentially the square root of x squared plus y squared and involving a Mach number factor. Here's an exponential, we always have exponential. And even in this form, we still have an integral, which in general is not known in terms of analytical functions. And this integral has to be evaluated numerically, and is evaluated numerically. Note one thing about this function. I took the y squared out. Why did I do that? That's to emphasize the fact that if I divide through by y squared to get k itself, this is a highly singular kernel. It's very strong. It's not like y to the 1/2, which I can integrate relatively easy. It's like y squared. And there's a very careful limit you have to take. You first of all have to consider what happens when z, that's the variable normal to the airfoil, is not zero, and then very carefully take the limit as z approaches zero. And there was a fellow named Mengler, a German during World War II, who figured this out. And then when Germany lost the war, Mengler moved to Britain and shared his wonderful knowledge with everybody else. And so he's the guy who did it. Okay, let's see. But for those of you who know about Cauchy singular values, Cauchy singular values is for something that goes like 1/y, This is 1 over y squared. So this is much, much more singular than a Cauchy singularity. The other thing I will say, there's a classical solution due to Theodorson. This was the first of the important developments in unstable aerodynamics. He has a method which uses complex variables, and in incompressible flow, we only need to solve the Laplace's equation. But the method he developed, which is wonderful and all that, only works for incompressible flow and only works in 2D flow. But other than that, it's great. And so it's an intellectual dead end in the sense that you can't take his method and do the 3D case or the compressible case. But it's wonderful, and as a tribute to Theodorson, it's included in the book. The other thing I'll say by way of human interest is that his daughter, Muriel Theodorson Williams, is a graduate of the Pratt School of Engineering, class of 1946, and she's still alive and well and living in Naples, Florida, and had her own career as an engineer. So it's a small world, as they say. Well, we have now covered, because you didn't ask me any questions, we have now covered both 3D supersonic flow and 3D subsonic flow. And the next thing we could have done, it's in chapter 4, we could have talked a little bit about transonic flow, but I'm not going to do that this semester. Instead, if he's willing, I'm going to bring in Daniel Levin on Tuesday, who's going to show you how to use a industrial strength computer code to not only compute the unstable aerodynamics on a wing, but also use that in a flutter analysis using either, I forgot whether they use the VG method or the PK method in that particular code, but one of those. And you'll have a chance to at least exercise, I hope you'll have a chance to exercise that code, and that will allow you to claim that you have done a real flutter analysis. Well, it's a beautiful day here. I'm about to go out and take a walk unless you have some questions. Questions for me? Oh, we need to talk about the final exam at some point, since we have a few moments. I'm still thinking we'll do a oral final exam, one-on-one, whenever the semester is over and the exam week is on us. And that'll be for an hour. Typically, there'll be about 3 questions. You can expect one on unstable dynamics. You can probably expect one on Hamilton's principle, Lagrange's equations. Maybe I'll ask you what is flutter, what is divergence, what is controlled surface reversal. Generally, I ask you a relatively easy question to start, and if you answer that, then I ask a harder question, and I keep asking harder questions until I find something you can't answer. So that's the general approach. Any questions about the final exam and or anything we've covered today? Last chance.
When will be the final exam? I don't know if I said those words in the right order.
Michael, do you know what's the official word at the moment? Do we know when the final, what is the week of final exams?
So the official schedule has yesterday being the last day of graduate classes. Next Wednesday is the last day of undergraduate classes. And then final exams is the week after that, give or take.
So what week is that? Are we talking about? Is that the last week in April?
Yeah, so that would be the last week in April, looking at between the when's reading week, guys? I think the 27th.
So
birthday final.
I think next Wednesday is the last day for graduate classes.
Yes, next Wednesday the 15th is the last day of graduate classes.
Okay.
Okay, and so what is the week of final exams then again?
I believe it's April 27th through May 1st.
Yeah, the 27th of April through May 1st.
Or May 2nd, yeah.
Okay, so I probably shouldn't ask you to attend any classes that week. But if it's all right with you, and I'm sure you'll be thrilled to do this, I do have some really good people lined up to give some lectures. So let's keep going until then. And then what I would suggest you do is send me an email telling me what hour you would like to do your final exam that week of April 27th. And let's see, we have about 9 people, I think. And I suspect not many of us are going to be going anywhere soon. So we should have a relatively open schedule in terms of when those final exams can be held.
What's the largest group size?
Say again?
What's the largest group size that we can have for the final exam?
Oh, and still do it oral?
The final exam,
yeah.
The final exam is going to be individual, so it's going to be you meeting privately with Dr. Dowell for 1 hour.
Yeah, that's right. This is just each student and myself will do an hour, presumably on Zoom. And what I would suggest is if you can arrange it, and this may be difficult for some of you, so let's talk about this. Normally what I would do is if we were doing this face-to-face is we'd be sitting in my office and I ask you to stand up on the board and draw some symbols and manipulate some equations and so forth. So what would be nice is if you have a camera where you can show me when you can write something that I can see it and we can talk to each other. Is that going to be possible?
We can also share.
There's a whiteboard function in Zoom.
Okay. That's great. I haven't used it myself, but I've heard that there is such a thing.
Yeah, they'll be able to show you their writing, Dr. Dowell.
I'm sorry?
They'll be able to show you their writing.
Okay, great. Well, this will be a learning experience for me too. But if you can do that, that'd be fine. So I'll say, here's an expression. In fact, what I'll probably do is I'll have my camera and I'll write down something and say, here's an equation. Tell me what you know about that, or sketch what looks like a flutter boundary or something. I haven't made up the exam yet, but I have done this once or twice before, so I have a general idea of what I'll do. So I'll have a camera here and I can show you some things I can scribble on, or maybe by then Michael can have trained me in Whiteboard, and hopefully we'll be able to communicate with each other that way.
Just one thing to add is that if you plan to use our webcams as cameras, the image will be inversed, right? Like will not be mirrored, so it will be a bit difficult to read.
There's a button within Zoom to mirror the display.
Okay, good.
Yeah, Michael, you and I probably need to have a training session where you show me what to do, and then would you like to volunteer to train any of the students who need help as well?
Yeah, I'll be around for any kind of technical support along the way.
Okay, fantastic. We'll all become more adept at Zooming. Okay, any other questions about the final exam or any other matters? Hearing none?
I have a question.
Sure.
How much is the percentage of the final exam compared to the homework?
I don't really do it that way. I just think about your homework and I think about the final exam. It's my experience that there's a strong correlation between people's performance on the homework and the final exam. But I don't have a magic number that I use to weight the two.
Okay.
How's that for dodging your question?
It's fine. It's just because we have to decide if they can pass or fail or letter grade.
Oh, that's right. I forgot. Michael, you probably know. Well, what are the rules on for graduate students? Students can. I don't think it's called pass or fail. I think it's called satisfactory or unsatisfactory. But in any event, what are the rules for graduate students?
Yeah, graduate students can opt. I believe. Are you guys opted? Are you opting back into grades and it's default pass fail, or
it's default pass and fail, and we have the option to get a letter grade or not.
So So right now all students are taking this pass fail, and then they can choose to get a grade. and you'll see this
Okay.
Dr. Howell on Duke
What-
you submit grades.
When do you have to decide that? When does the student decide
Next
which way
Wednesday.
they want to go?
Next Wednesday.
Next Wednesday, okay. So by next Wednesday, you will have decided, and in principle, I will know whether you're doing it one way or the other.
Yeah.
Yeah. No, I shouldn't say anything more about that. Because I know, knowing this group, I know that you're not really interested in grades. I know you're really doing this course because you're seekers after knowledge and you know how much this is going to benefit you years from now. Is that true?
You know it so well,
Se-
Professor.
Seekers of knowledge and degrees now.
Yeah. Well, you decide what you want to do about the grades in terms of pass, fail, or I think it's really called satisfactory and unsatisfactory, isn't it? Someone told me that there was a subtle difference between pass, fail versus satisfactory and unsatisfactory, but I've forgotten what it is. Or on the other hand, you can opt for a letter grade, and I'm happy for you to do whichever one you want. Other questions?
So as a reminder, homework 10, the typo identification is going to be due next Tuesday, April 14th.
Yeah. Yeah. And I think Danny is prepared to assign you a homework, but the homework assignment is really to use this commercial code. And we have what is called the educational version, which isn't quite as powerful as the one that Boeing or Airbus has, but it's sufficient to show you how it works. And I think you'll have a homework assignment which will exercise that code, and I think that will really be interesting for you. Students in the past seem to have found it interesting.
Sorry, Professor, there is only a little problem. We have no access to Duke computer facilities. So.
Oh, is that right? Okay. Well, we may have to go to Plan B then. I wasn't sure about that. I was hoping that you could get into the Duke computer system.
We'll help the students set up with Educational Zero next week.
Okay. You think we can do that?
It should be possible on individual computers.
Okay. Well, you and Danny, I think we're going to have a conversation if you haven't had one already. Let's see what we can do, because I think that is a good experience, and it is more work, of course, for the students. But I think it's something when you're going through your next job interview, if you can say I used Z-Arrow and did a real flutter calculation, I think that'll give you at least another $10 a week in your salary, I'm sure, maybe even more. Other questions? Hearing none, I wish you a very good day and enjoy the rest of it.
All right, enjoy your walk. Thank you.
Okay,
Professor.
we'll see you on Tuesday.
Thank you.
Or hear you on Tuesday, at least.
Thank you.
Thank you.
Bye-bye.
Thank you. Bye-bye. Michael, are you still there?
Yes, indeed.
Any thoughts or questions? Anything I should be thinking about? Oh, by the way, I really like your paper. I sent you an email and a scan. I don't know if you've gotten that yet or not.
Yes, I saw that.
Yeah, but that was good. That is good.
Thank you very much.